So welcome everybody to Hoon Academy Lesson 7. So this is going to be our penultimate lesson of Hoon Academy. Next week is going to be our last lesson, okay? So we're in the final stretch of the course, and at this point, we've gotten a good look at the fundamentals of how Hoon, the programming language, operates. Let's start this lesson by zooming out and getting a bigger picture of how your Urbit computer works. Okay. So Urbit, as you may know, is pretty unique among computer systems for a variety of reasons. And one of those is that it's a clean slate operating system. The entire system is about 30,000 lines of code, which is tiny in comparison to something like Windows, Linux, or Mac OS. Okay. The system is completely accessible to read and examine, and an individual could even come to understand all the parts of it, which cannot really be said about any other operating system in use today. As an Urbit user and a developer, this gives you a degree of autonomy because your computer becomes something that you not only use, but you can understand and even modify. So start poking around. We're going to go to our terminal, and then we are going to run rmount send base. Okay, and that's going to make the base folder show up on Earth so that we can take a look inside and start poking around. Okay. Now, let's go into our base folder. And in here, we can see several different folders. Okay. So far, we're familiar with this gen folder. That's something we've used before because we've put generators in there. We put reusable scripts inside there. There's several other folders here. So the lit folder contains library files, which are like utilities that you can import and use in your other code. You may be familiar with libraries from other programming environments. The app folder contains the core logic of every app that is installed on your Urbit chip. The SIR folder contains structure files, which are like custom data types that your apps use. Okay, so the SIR contains structures that your apps use. And the MAR folder is going to contain what are called MARC files, which define basically file types on Urbit. Okay, like on your computer, like the equivalent of .pdf, .txt, .jpg, right? So on and so forth. Those are defined in the MAR folder. Transient stateless computations. We won't get into them too much in this course, but certainly that's something you can learn about in our next courses. Okay. So none of these folders that we just talked about contain the core system logic of the computer, and that is going to be contained in this sys folder right here. So let's take a look inside this sys folder. All right, let's go in here, and we're going to see that there are 4 files here: arvo.hoon, hoon.hoon, lol.hoon, and zeus.hoon. Okay, so what are these 4 things? So first off, let's take a look at hoon.hoon. This file is going to contain hoon.hoon is going to contain the primitives of the Hoon language. It's going to contain the compiler and contain the standard library, which you are used to calling from to use things like add and comparing numbers and all those utilities that we use, right? Next, there's going to be arvo.hoon. Arvo.hoon is going to define the fundamental event processing machinery of the OS. So the very, very core kernel of the OS is going to be defined in this arvo.hoon file, okay? Next, there's going to be lol.hoon, which is going to contain some type definitions that Arvo uses, okay? So this is mostly system stuff that Arvo is going to use. And finally, Zeus.hoon is going to contain libraries which give you tools to deal with cryptography, formatting, JSON, HTML, and stuff like that. So these are like utilities functions that are used by the system, okay? So each of these files is going to be one big core. And these big cores are going to be composed with each other to form the standard Hoon subject. So recall that I mentioned whenever you type something, whenever you type a piece of code in the dojo, it's going to be implicitly composed with the standard dojo subject, right? And now we can understand exactly what that is. It's formed by taking these four files and composing them against each other. So you take the Hoon.Hoon core, set as a subject, and then build Arvo.Hoon, then you take that and set it as a subject, build make these four cores nested inside each other, inside of the right hand, the payload side of each successive core, right? So that is how the standard dojo subject is formed. And whenever you type any dojo expression like send less, add 2, that's actually going to be substituted right here in this chain of compositions, okay? So there's one more thing in this sys folder that we haven't looked at yet, and that is this vein folder. So what's going on in there? Veins are like kernel modules. They're different parts of the operating system that can be plugged into Arvo to do different tasks, okay? So if we go in here, we'll see several different files, each of which corresponds to a different vein, okay? So what do these things do? Gal is the vein that handles apps, okay? That's the logic that apps use to interact with the Urbit system. Clay is the file system, okay? Dill handles the terminal, the dojo, and Bane is going to handle setting timers, okay? So all these have a different task, and these just plug into Arvo basically. And you can even add more of these if you'd like. For example, the vein con, which handles Urbit's communication to external devices, that was actually added within this year. That was built and added within this year. All right. So any questions on that? Okay. So in the next part of the course, we're going to go here and we're going to go to this very important file, Hoon.Hoon, okay? And we're just going to take a leisurely scroll through that and see what kind of important things are contained in this file, which is part of our core operating system. All right. So as we mentioned, Hoon.Hoon is going to contain the definition of the language, of the compiler, and the standard library. It's basically the backbone of our Urbit system, okay? And it's going to be organized into chapters with this lust bar room. This just tells you like we're separating out this giant core, which has thousands of lines into chapters, just to add some organizational help. So this is the math chapter, and there is there are more chapters. Okay. We're going to go through a couple of these. We're not going to go through this whole thing. Okay. And if you're ever looking for documentation on this, you can always go to this link, which I'll put in the chat right now. That's our entire Hoon reference documentation for the standard library. So basically documents what's going on inside this file. Okay. So chapter 1A of Hoon.Hoon, basic atom arithmetic. This is stuff we have used before. It's that your add, mul, gth, lth. It's all created and defined inside of this chapter. In fact, if you look right here, you can see the source code for gth and div and so on and so forth. All right, so it's all right here. So we're familiar with how to use this, right? Next chapter, chapter 1B contains some basic utilities to work with trees, since trees are the basic data structure of our urbit. It's useful to have some utilities to deal with those. For example, if say you have a tree and we're gonna say what's the address inside the entire tree if I go to the subtree rooted at number 3, and then inside there I go to the subtree rooted at number 4. So if we consider this as the root of the tree, and number this as 1, then it would be 1, 2, 3, 4. So less 4 inside of less 3 is actually less 12 inside of the whole thing. And instead of like doing this calculation or drawing it out, you can actually just use this utility called peg. So peg 34 is going to tell us that the address of axis 4 inside of axis 3 is going to be 12. Okay. So there's a couple more utilities that are like that inside chapter 1B, working with trees. Okay. So next, chapter 2A contains the logic for working with units. Okay, so what are units? This is a new concept that we're about to learn. So recall that in Hoon, the character sig, that actually stands for the value 0, right? It's not a null character, it's just a window dressing over the number 0, right? So if we cast the sig to a pat, we can see that. This is telling us that the data underneath this symbol is 0. Okay. So imagine that we are creating a database for a bank app in Hoon. Okay. So in this database, you have keys and values, and keys are going to be people's planet IDs, and values are going to be their associated how much money they have, right? Now, if we have this key value store right here, and we query our app for Wes, we're going to get a 0, right? And that's because he has $0. Now, if we query for Sev, who is not a customer here, that's Sev is not a Pat P. Well, we need some way of saying, hey, Sev's not in our customer list, right? You could also return a 0, but then that would be confusing because you get customers that have $0 returning a 0 and customers who are not in your database returning a 0, and how do you differentiate those two, right? So that situation is exactly why units are useful. Okay. So what are units formally? Formally, a unit is a mul generator, just like list. It's a gate that takes a type and it creates a new type, right? So remember that if you do senhep list pat p, or just list pat p like this, that creates a new mul, a new type, right? Which is a list of pat p's. And the term unit works the same way. If you do senhep unit pat p, that creates a type which is a unit of a pat p. And what is that? A unit pat p is going to be either just the sig, it's either just the sig, or it's going to be a pair of sig and some pap p. Okay. So for example, just sig is a valid example of a unit pap p. Also, a pair of sig and sample palnet is a valid example of a unit pap p. But just sample palnet is not a valid example of a unit pap p. Okay. Does that make sense, everybody? Okay. So imagine using this in our bank account example. If we queried Wes, we would like to receive not just 0, but actually the pair sig 0 as our output. If we queried Bud, we get the pair sig 8.639. And if we queried Sev, who is not in our database, we would get just the sig. All right. That makes sense, everybody? All right. So there's no questions. We shall be moving on. So let's go over some utilities that help us use units. Okay. So the library gate sum can take a value, sample palnet, get a unit of sample palnet. Okay. If you have a unit and you need to get the value out of it, you can use this need. So need this unit, you get that sample palnet out of there, right? If you give need an empty unit, there's no value to extract, then it's going to crash, right? There's also a sugar syntax, which if you just put this tick in front of some value, it'll actually put that into a sig and that value. However, you do need to be a little careful here because remember, when we were learning about lists, just like the cell 123 sig is not necessarily a list, a cell of sig and sample palnet is not necessarily a unit unless you typecast it and prove that in fact this is a unit that you're working with. Okay. Finally, there's one more useful utility for working with units, and it's called bind. So suppose you have some gate like add. So say I have the numbers like 2 and 3 in units, right? And I want to add these two in unit values together. So one way you could do it is you extract the unit, the value out of the unit, and then you add them, and then you put it back in the unit. But that's a lot of steps, right? So bind is going to help us be able to work on units. It makes regular gates that work on values work on units. Okay, so for example, if we do so to use this, we're going to bind this add gate and we're going to pass it 2 and 3 inside of units, like here. And then we're going to, oh, sorry. You have to pass it the input as one thing. So we're going to pass it the 2 and the 3 inside of a unit, and we're going to get a result of 5 inside of a unit. Okay, so we're just taking that add and making it work on units instead of add, which regularly works on values, right? If you give this an empty unit, then it's just going to return sig. There's a bunch of other unit utilities, and we don't have time to cover them, but what the library offers to work with these data structures. Okay. So let's go onwards. Let's see what else Hoon has to offer. Okay. Chapter 2b, the list logic library. Basically, we covered this pretty thoroughly in lesson 4. Lesson 4, we learned how to work with lists and text, if you recall. Right. Chapters 2c and 2d deal with bits or manipulating data stored as raw zeros and ones. Okay. Next, we should cover chapter 2h, which deals with set logic. Okay. So, what are sets? Suppose that you're throwing a big party, and you want to keep track of who's on the invite list, right? And as the party approaches, you're adjusting the invite list. You're maybe adding some people, you're deleting some people. You want to make sure that list is right? But if you actually use the list data structure in Hoon to keep track of that, list can have the same value twice, right? List can have the same values as many times as you want. So if your list had Alice twice on it by accident, maybe that would make your Urbit app send 2 invitations instead of 1, right? So we'd like to have a data structure that actually imposes a uniqueness upon our data, and that is what sets do. So a set is an unordered grouping of data. So in contrast to lists, which have an order, sets are not ordered, and sets maintain that each data structure, each data in it must be unique. Okay. So just like the term list, the term set is a mold generator. It takes a type as input, and then it creates a new type, right? So if we want to make a set of the type that is a set of tapes, we do have set tape, right? Or like this, set tape, right? So let's learn how to make some actual sets and how to work with them. So the library gate silt is going to let you make an instance of a set from a list of things. Okay, so let's see this code, which is going to take this code is going to take a list of Alice, Bob, Charlie, Alice, Dave, and convert that to a set of tapes. Okay, so and note how the input list had Alice twice, but our output set only has Alice once. If we don't do this casting here, we'll actually get the raw data structure underneath, which is the same data structure. It just looks messier. It has these like N, I, L, R, and that just basically the sets are implemented on a tree structure underneath. And this is like kind of the more raw data structure, which implements a set. But this and this are the same thing. Okay. So let's learn how we can work with sets. Um, before we get into it, we need to take a quick detour back to something that we learned in lesson 6 in last lesson. Okay, so recall that in last lesson we learned about a door which can build a gate representing any linear equation. And if you've done the homework, you've seen the homework question which asks you to build a door representing any quadratic equation, right? So the code looked like this. And let's go over again what the different parts of this piece of code do. Okay, so we're gonna, it builds a general class of gates that represent any equation of the form ax plus b. Okay. So the outer door has a sample, which is a pair of parameters a and b, which are both PAD-UD numbers. Okay. Next, that door has a single arm, and that arm contains this gate as its content. Okay. That gate takes a single argument x, which is a PAD-UD. It enforces that its output must be a PAD-UD. And inside of the gate, it uses these parameters that are passed in from the outer door. Okay. And it computes ax plus b. All right. So we can take this code and we can use it, for example, to, if we call this linear, then we can call linear with the parameters 4 and 2 to create a gate which represents the linear equation 4x plus 2. Right? And then we can take that gate that we built and then pass it an input of 1 to get 4x plus 2 with the value 1 passed in for x, right? And that's going to give us 6. So why did we cover this? Going back to sets, when we work with the set library, we're actually doing the same pattern here. So we're going to work with a door called in, and this door takes a set as a sample. This outer door takes a set as a sample, and then inside of it, its arms build a bunch of gates. Okay, and each of those gates take that parameter, that set that you passed in, to build itself and define its function. Okay. So let's go through an example of this. Suppose that we have our party set, and we want to add somebody to the set. All right, we want to add somebody to our invitations. We can use the put arm of the in door. Okay, and when we call the put arm of the in door with our party set as a sample, this creates a gate. The output of this is a gate. That gate then takes an element and then returns a new set with that element added. Okay, so let's see exactly how to use this. So we're going to define our party set, and then we are going to create a gate by calling the put arm of the indoor with our party set as a sample. This is a gate, and then we're passing that gate a new thing to add to the set. And finally, we're casting that output again back to a set of tapes. And then we are going to get our new set with Edward added to it. Okay. Does that make sense to everybody? I'll put this code in the chat for you guys. So again, we're creating our set in this line, and we're calling it party. this syntax means call this arm of this door and pass in this sample to the door, okay? So the door gets the sample, and this is one of its arms. That arm builds a gate with this parameter. And so the result of this is a gate, which accepts a new element and creates a new set. And that's why the result of this is this new set. All right. So let's see another example. So suppose that last time you had a party, Dave puked everywhere and set things on fire. So sorry, Dave, we have to uninvite him from the party. Okay. So you can do that with the del arm of the indoor. So again, we're going to define our party set. And then what we're going to do is we're going to call the del arm of this door with a sample. This builds a gate, and that gate takes an element and returns the set with the element removed. Okay. So, boom. Alice, Bob, Charlie, Dave's not there anymore. Suppose if you want to check if somebody has been invited to your party correctly, you can use the has arm of the indoor. And this syntax will return a gate, which takes an element and then returns a send.y or a send.n if the sample set has that element or not. Okay. So again, we define our set. And then we call this gate that we built with the input Frank, and we get a no because Frank is not in the set, right? If you do the same thing and then we call Bob, we're going to get a yes because Bob is in the set, right? Some other things we can do. We can convert set to a list with a tap. And here, this syntax doesn't build a gate. Since you don't need to give any more inputs, calling the tap arm of the indoor with this sample is just going to give you that result. It's just going to give you the full set converted to a list. Okay, so same thing, we're going to define our set. And then we do path in party. Then we're going to get this as a list. If you want that to be formatted more nicely, you can cast it to the list of tapes and then there. So now notice that we started with a list that we converted to a set with this silt function, and then we converted it back to a list. And there's a useful trick here, because if you ever have a list that you need to deduplicate, you just want to get rid of any duplicates in that list, you can convert it to a set and then convert that set back to a list, and you get that list with duplicates removed. Okay. All right. So
is that double angled brackets notation new? Because I swear list one represented like that before.
yeah, so the double angled bracket notation is because I think it's because a list of tapes is like a privileged, it's like a particular type of data that has its own name, but this is in fact just a list of tapes. It's like Charlie, Bob, Dave, Alice, Sig. It's just the pretty printing by the dojo.
Okay.
Good question though. Something else you can do if you want to apply a gate to all elements of a set. So suppose that we want to take all these names and we want to capitalize them. We can use this run, okay? This run arm. So this syntax will create a gate, which then accepts a gate and then returns that set with applying that gate to all elements in it. So I'll show you what I mean. if we create our set and we do run in party, and then that creates a gate, which we then pass another gate like cuss. Remember, cuss takes a tape and capitalizes it. So this is going to return our set with every name capitalized. Okay. So there's a lot more of these utilities. We can't go over all of them, but hopefully this gives you an idea of what's available and what's possible when working with these data structures. Okay. Okay. So let's move on. Chapter 2I of Hoon contains map logic, and maps are another important data structure that we should learn about. So key value pairs, or what's called dictionaries in other languages, or what's called maps in Hoon, are very important constructs. They let you store data under a key and then search that data up later by referencing that key, right? So in Hoon, the term map is a mold builder, just as if you call map on two different types, it's going to create a type which is a map with this as a key and this as a value. So in this case, this syntax creates a map with pat t as a key and pat ux as the associated value stored under that key. All right. So if you want to create an instance of a map, the library gate mult, if you pass that a list of pairs, key value, key value, key value, it's going to create a map for you with the keys and the values. Okay, so let's see an example of this. Suppose that you're making an Urbit app and you need to store and render some colors to be displayed on your front end. You could do this by making a map from pat t piece of text to their hexadecimal representation, which you need to store and then send on to the front end, right? So let's take a look at this piece of code right here. What we're doing. So mult, that's this gate right here, takes a list of pairs, a bunch of pairs of keys and values, and creates a map from those pairs. Okay, so we're going to create a map with red and then this associated hexadecimal, green and this associated hexadecimal, and blue, and so on and so forth, right? Press enter and we get this as a result. The output here, which looks a little messy, is referencing the underlying data structure that the map is implemented on. Okay, but this output does in fact mean our map has been built. We can verify this if we like by using our cathep, which is a type check. So we want to verify that this is indeed a map from pat t to pat ux. And this piece of code, and it passes. So we have created a map from pat t to pat ux. Okay. So how are we going to use this map? Let's go over some library functions that let us manipulate this. Okay. So one of the things you might want to do is put another thing in, put another pair in your map, right? There's a standard library gate. Sorry. So the door by, just like the door in for sets, the door by is the door for working with maps. Okay. And this door has a lot of different arms, which do different things. Okay. So if we want to put something in our map, we're going to call the put arm of the by door with our target map as the sample. Okay. And the syntax creates a gate. And then that gate takes a new key value pair and then returns our new map with that added. Okay. So let's see this in action. Let's create our original map and call it colors. I'm going to call this colors. Okay. And then we're going to call the gate produced by put by colors on the pair yellow and its associated hexadecimal. Okay, we press enter, and then now we see that yellow and its color are in there. Okay, so I'll drop this in the chat for you guys. So what else would you like to do with a map? You probably like to be able to delete things from it. So the del arm of the by door is going to do that for you. Calling this syntax is going to create a gate, which takes as input a key, and then returns the new map with that key and its associated value deleted from the map. Okay, so let's create our map as before, and then let's run del by colors on input green, and we'll see that the output only has blue and red, no more green. Okay. If instead of something that exists, if we pass in a key that does not exist in the map, we'll just get the map back as it was before, unchanged. Okay. So what else might we like to do with maps? We might want to look up some key and see what value is contained in there, right? So the get arm of the by door is going to do that for you. So if you call the get arm of the by door with a sample of colors, this creates a gate. That gate takes a key, and if that key exists, then it's going to return a unit. Okay, so remember, we just learned about units. This is exactly the situation in which units are most useful. Okay, so if that key exists, you're going to return the value in a unit, and if that key doesn't exist, you're just going to return the sig. Okay, so let's see it in action. Let's find our colors map, and then if we do get by colors, creates a gate, and then you pass that gate red, then you'll get your hexadecimal in a unit. All right. If you ask it for something that does not exist in the map, you just get the sig. Right. So the gate got works just like get, except that it doesn't give you back a unit. So if something doesn't exist, it's actually going to crash. So if something exists, you get it back. If something doesn't exist, this code will crash. So this, you got to be a little careful using this one, because imagine if somebody just wanted to look up some data in your app and that caused the app to crash. Usually people like to use get for that reason. You can use got if you're sure that something exists. So show you an example. Let's find our map. And then if we do got by colors red, you just get the hexadecimal back directly. And if you do got by colors orange, which does not exist as a key in this map, you get a Hoon expression fail. Okay. A few more things you can do. You can convert a map to a list of pairs. So you do tap by colors, you get this map back as a list. You can do val by colors to get a list of just the values. And you can use key by colors to get a list of just the keys. Okay, so different ways to extract your data from your map, right? So just like with lists and sets, there's a very rich library of utilities to work with maps that we cannot cover in the limited time that we have. But if they're all in the documents, if you like to look. So moving on to the next section. So chapter 2N of Hoon contains some functional hacks, some tricks that let you do functional programming stuff. Okay. So if you do have some programming experience in other functional languages, then some of these may look familiar. And if you don't, then that's perfectly all right. So what's the first thing that we should cover? It's curry. Okay. So what does curry mean? Curry means you take a gate in Hoon, and then say your gate has three arguments, right? 1, 2, 3. You're just going to take one of those arguments and say, this is always going to be some fixed value. You're going to fix that argument to something. That's going to give you a new gate, which now takes 2 arguments instead of 3, and one of those arguments is now like set in stone, right? So that's what CURY does. It takes a gate, substitutes a value in for the leftmost part of the input gate sample. Okay. So, for example, if we want to make a new gate which multiplies a value by 10, we can do CURY mul 10, and this creates a new gate that we'll call mul-10. Then we can call our new mul-10 gate on number 5, and we'll get 50. Okay. Any questions on that? So again, we're creating a new gate by substituting in a value and fixing it to something for another gate. Okay. So CURR works just like CURY, except it binds the rightmost value of the gate. Okay. So, for example, we can, if we want to create a gate, which will tell you if something's bigger than 10, you can cur GTH with the value 10. And let's call that GTH 10. Then you can ask GTH 10 11 and get a yes. Fork is going to let you compose 2 different gates, right? So take 2 different gates, which are like functions, they're like pipes, and you just glue them together into one big pipe. So, for example, if we're calling our text functions, suppose that we want to reverse a tape and convert it to and capitalize it at the same time. Sorry. Suppose that we want to capitalize a tape and convert it to a chord at the same time. So we're going to use Quark to combine these 2 text gates, and then we're going to do both those things at once, right? There's one more functional trick that we should learn, but it's not in a standard library. It's actually a rune. Okay, so the rune mickcol makes it possible to run a gate which usually takes 2 arguments, like add or mul, or so on. But you can actually then pass it as many arguments as you need. All right. So, for example, if I do mickcol mul on 1, 2, 3, 4, 5. So mul usually takes just 2 arguments, but now you're passing it in 5 arguments, and it's going to work, and it's going to multiply those all up through. Okay. And the sugar syntax is going to look like this. You just put this this mic in front of, oh, sorry, you put the col in front of this parentheses. And then just like that, you're multiplying all those numbers up together. Okay. You can also use this with welding tapes together. And boom, you've done all those welds in one step. Okay. All right, any questions on functional tricks in Hoon? All right, so moving on. In Hoon, chapter 3b is going to be your section for dealing with floating point numbers. Now, what are floating point numbers exactly? Floating point numbers are how computers represent numbers that aren't just whole positive numbers. So, for example, negative 3.333, 25.5, pi. Now, all these numbers are not just positive or whole numbers, right? Hoon actually has several different representations of floating point numbers, and each of these has associated library utilities. Okay, so if we go to the link for the standard library, you can see all of these representations. Right? Okay. So what's going on in on this page? So there's this Fn, Dn, and Rn. All of these are ways to represent floating point numbers where it's broken into several different pieces of information. For example, like one piece of information might represent the sign, one might represent the exponent, and so on and so forth. Okay, so these represent numbers as a cell, as a not as an atom, not as a single bit, a single piece of information. Right? However, there are ways to represent floating points as single pieces of information, and those are these four auras right here. Okay. So these auras that start with pat R are going to be your floating point auras. Pat RH is going to be half precision float, which uses 16 bits of information to represent a number. Pat RS is a single precision float, which uses 32 bits. Pat RD is a double precision float, which uses 64 bits. And our quadruple precision float, Pat RQ, is going to use 128 bits to represent your floating point number. Okay. And the reason to offer these four is you can pick and choose how much precision and how much data you want to use. Right. In Hoon, you'll often see floating point numbers represented like this. And here's how to read the different parts of this piece of data. Okay. So the leading dot indicates that we're going to parse this number as a floating point and not as a whole number. Okay. This negative here indicates a negative number. If it's not there, then it's a positive number. Here, this is the actual numerical contents, which is 2.5 in this case. And here's the exponent, which indicates the exponent of this number. In this case, e negative 3 means that it's 2.5 multiplied by 10 to the negative 3. And if you recall, 10 to the negative 3 means 1 over 10 times 1 over 10 times 1 over 10. That's 1 over 1,000. So in this case, we're multiplying negative 2.5 by 1 over 1,000. Okay, so number is negative 2.5 times 10 to the negative 3, or negative 0.0025. Okay. We have all the library utilities that you'd expect for manipulating these kinds of numbers. Okay, so for example, you can add two floating points. Here we're adding 2.5 times 10 to the negative 1, or sorry, times 10 to the 1, plus 2.5 times 10 to the 2. Okay, that gives us 275. This syntax right here, we've seen this syntax before. Remember that this is sugar for this room. Tis gal add rs, which means that rs is a core that we're setting as the subject, and then we're going to pull one of its arms and build it. We're building that add arm of the rs core, which contains our utilities for working with these floating points. Okay. If we want to divide two numbers, we just use div col rs, the div arm of this rs core. If you want to compare the sizes of two floating points, you can use gth from this core. So this pretty closely mirrors what we've seen with our pat uni numbers. All right. Any questions about floating point in Hoon? All right, so we're getting close to our end of our walkthrough Hoon.Hoon. Obviously, there's a lot more stuff, but this is just a general overview. Chapter 3C of Hoon.Hoon lets you work with time in Urbit, the PAT-DA data structure, the PAT-DA aura. Chapter 4B contains some text processing utilities that we've seen before, like CAS and CUS and SANE. Those all live in chapter 4B. Okay. So let's wrap up our discussion of the standard library by briefly covering some syntax that you might find in the WoW when looking at Hoon code. Okay. So these four symbols, these represent types. These are shorthands for different types. So far, we've seen this pat, right? This symbol represents the most generic mold for any atom for any single value is going to be a pat. Okay. There's also three more of these. This ket is the most generic mold for any cell, any pair of values. This tar, this is going to be any possible noun. So any possible, whenever you see this tar, that means a type that is as expansive as possible. It can be any piece of data. And finally, this question mark is going to be the mold for a Lubian, a yes or no. Okay. So we can prove this by bunting them to get their default values. So for example, we can use the ket tar rune to bunt this ket and get the default value for a cell, which is just the pair 0, 0. We can get the default value for a noun, which is just the value 0, and we can get the default value for this alluvian, which is the value yes. Okay. So Urbit says yes by default, I guess. Okay, so any questions on those? Those are just shorthands for different very generic types. Okay. All right. A few more different kinds of syntax. These, if you ever see these, they look like mathematical operations, but they're actually not mathematical operations. They are shorthand for operations in Hoon. Okay, so A plus B, it's not adding up numbers. So if you do 1 plus 2, you're actually going to get a cell of sen 1 and 2. Okay, so that's useful if you ever need to like because these head tagged cells are very commonly used in Hoon. So for example, if you do dog plus Dashun, then you get a cell of send dog and Dashun. If you do cat plus Maine Coon, then you get a cell. And this slash, this FAS symbol is actually doing the same thing. And this ket in between two values, it just makes a cell. Okay. So just to give you a heads up, if you ever see these, they look like math, but they're not. Okay. All right. So in this lesson, we move towards a greater understanding of the Urbit system and the Hoon language as a whole. And finally, in our next lesson, our last lesson of the class, we're going to conclude the course by learning how do we build production quality code. And we're going to understand the system even a bit more by hinting towards what's next in our upcoming, our future classes, where we can understand the core system and understand the structure of apps. Okay. So yeah, thank you for being here for lesson 7. See you next time.